Okay, so this is all about estimation error, right? But there is one more piece of the puzzle which we have completely kind of have been ignoring so far, and I just wanted to make a couple of statements about that as well, which is the final piece of the puzzle. Piece of the puzzle, which is the approximation error, which is to look at the difference between RT of H and R star, right. So, this is the least test error in H, this is the base error, which is the least test error if H is the entire set of functions. Now, one might ask, why are we even restricting H, right? So, why should I restrict H to be linear? Why should I restrict H to be maybe quadratic or anything of that sort, right? So, why am I doing that restriction? Well, I am doing that restriction so that all the other statements that I made about generalization error and estimation error make sense. If I do not restrict H, if I allow H to be the class of all functions, then what breaks down? Can you pause and think about this? Or if you already know it, I mean, which means that if you've been following it carefully. So, if we do not restrict our class of functions, then we do not have a generalization bound, we do not have an estimation error bound, and that is because our VC dimension arguments break down. If H is the set of all possible classifiers, then that hypothesis class has what VC dimension? It has a VC dimension of infinity, and so these kind of statements that the max H RS of H minus RD of H is greater than or equal to epsilon by 2, it cannot be controlled, right. So, we cannot say this is less than delta, right. So, for if n is large enough, we cannot make such statements because that is too huge a class to make such a statement. So, we will not be able to do that. So, which means that I have to, there is no other way but to restrict H, right. So, and the moment I restrict H, then whatever algorithm that I use is going to be useful only within that H, because I am picking something from this hypothesis class, right. So, I have a restricted bag, a linear hypothesis class or a quadratic or whatever that class may be, but we have fixed that, and that is where we are searching in. Now, our true error minimizing hypothesis H star, the true H star, the base error, base classifier may not be in the hypothesis class where we are searching, right. So, it might be outside. On the one hand, we cannot make H the set of all classifiers because our bounds will break down. On the other hand, we cannot make it too small also, because then we would have good generalization error, good estimation error, but then we might have a big approximation error, right. So, even if you use an ERM in H, right, so we might still have a big approximation error. So, how do I solve this problem? Well, in a statistical learning sense, what is suggested by Vapnik to solve this problem is to move away from ERM and do what is called as SRM, which is structural risk minimization. And this was Vapnik's proposal. So, let me tell you that proposal and then we will talk a bit about that. The proposal is the following, right. So, I have H, which is the set of all possible classifiers, and now what I am going to do is I am going to have a nested set of increasingly complicated classifiers, right. So, let us say this is the set of all classifiers. Right. So, let us say this is a set of all classifiers, and then I have a nested set of increasingly complicated classifiers. Now, Vapnik's suggestion was to do the following. The suggestion was, perform ERM here with H1, right. So, let us say this is linear, the second one is quadratic, the third one is cubic, and so on and so forth. So, if you perform ERM and let's, for the moment we are still going to assume that ERM is possible, hypothetically, right? So, because we can then reason about it and then we will worry about, calibration etc. later, but for now assuming ERM is possible. So, I will do ERM here, I will get H1, if I do ERM here I will get H2, if I do ERM here I will get H3 and so on and so forth. Now, as the H becomes more and more complicated, of course, my training error is going to go down, because H2 contains H1, which means that if I am searching in a larger space of classifiers, I am going to get a classifier which potentially has lesser training error, because I am doing ERM there as well. So, the train error goes down, but then the complexity of these classes keeps increasing. So, at some point what is going to happen is the classes become so complex that I will do overfitting, and so I will not generalize or I will not have good estimation error, right. So, somehow we need to balance these two things, and the proposal that was given was to do was to look at ERM plus some penalty, and then find that H which minimizes ERM plus this penalty term. So, in particular Vapnik's suggestion, and this we can prove something about this particular choice, was to do the following, right. So, you do HI ERM, RS of HI ERM, which means that this just means arg min over all H in HI RS of H, okay, plus, and let me put down this term. So, this looks like di log n over di plus log 1 over delta by n, right. So, we are not going to really prove this, but this is basically the penalty term where di is just the VC dimension of HI, right. So, basically you have an increasingly nested set of classes whose VC dimension of course is going to also keep increasing, because more the classifiers, the more the chance that player 1 will win, right. So, because remember VC dimension, it was between player 1 and player 2. Now, however player 2 smartly labels it, player 1 should pick a classifier and then show that it labels whatever player 2 has labeled. Now, if you have more classifiers, you have more chance of winning the game. So, the game will proceed to more rounds, and so VC dimension will keep increasing. So, this will be less than or equal to this, less than or equal to this, and so on. So, now that appears as a penalty term basically, right. So, the penalty term has this VC dimension, and what Vapnik was able to prove was that when you do this, then as you get more and more samples, then your approximation error also goes down to 0. So, remember what the proposal is as follows, right. So, first of all I have to come up with this way of arranging H1, H2, H3 and so on. It could be linear, quadratic, cubic, etc., etc., but I should be able to separately perform ERM for each of these. First I will do ERM with respect to H1, I will get with respect to script H1, I will get the classifier small h1, I will note down its training error, and the second term is something that depends only on the VC dimension of H1, the rest are n and delta are all fixed for all the H's. So, I can compute this value for H1. Now, next what I do is I will again run the algorithm, but now I will do ERM with respect to H2, I will get small h2, and now again I compute this, and then over all this I am going to find that H, that ERM with respect to whatever HK is, which minimizes this quantity, right. So, that was Vapnik's proposal. And if again this is also computationally not possible, first of all ERM itself is not going to be computationally possible. Now, we are asking to do not just one ERM, but then multiple ERMs across different hypothesis classes. Now, this is not again not practical. So, in practice as a proxy, this effect is indirectly achieved, right. So, somehow you want to control the space from which you are learning by penalizing the space. the hypothesis class from which you are learning, and the way that is controlled, usually in practice, we use regularization, right. So we might, in practice, we might solve something like, I don't know, minimize over W, even if it's a linear thing. So we might do sum over I equals 1 to n, some loss of W transpose xi comma yi, whatever that loss is. It could be the logistic loss, hinge loss, exponential loss, whatever that loss is, plus maybe we will do some lambda times norm W squared, right. So this would be the regularization, right, regularization. Now you can think of it as somehow this regularization indirectly affects the space in which you are searching, right. So in other words, you might potentially use map, and let's say if you remember kernel methods, right. So you might potentially map xi to a very high dimension, which means that if you are learning a linear classifier in a very high dimension using like a polynomial kernel of degree d, degree k, then that means that essentially you are learning in hk, right. So linear in, after you map xi to phi of xi, would look like, in the original space, space of all possible polynomial functions of degree k. Now that will have a bigger VC dimension, but now because I am doing this regularization, I am effectively making a lot of W's smaller or close to 0 depending on the type of regularization you use, L1, L2, etc. So effectively what I am saying is that I am not really learning in the original HK, but then in a smaller space. And where exactly will I learn is directly controlled by this lambda, and that is a hyperparameter, which cross validation will help us. So in practice, in spirit we are doing structural risk minimization, where the spirit of adding a penalty term is there directly in the optimization, but not doing separately for each of HIs, and then adding the penalty term post hoc after you get the classifier and then computing a number. You can incorporate that directly into the problem itself, right. So that's what people do in practice. Okay, again one can prove results about this form, which we won't do that, but just to illustrate that, now you can break down the original question you asked about, how good is this training error with respect to the base error. Now we can control using ERMs or SRMs, generalization error, estimation error, and also approximation error. And so SRMs are kind of the best thing to do in some sense, but you have to be careful about how you are regularizing and so on, because it's an indirect method, right. So that's kind of at a high level one way to look at this learning theory. So we'll look at a slightly different viewpoint of statistical learning from a completely different lens, which is a very interesting lens. We will start looking at that next. Thank you.